This is a video on calorimetry, and so calorimetry is really interesting. It's basically the process of allowing something that is really warm or even going through a chemical reaction to release a bunch of energy into a surrounding environment of water. And the reason we might want to do something like this is to identify the specific heat of a substance, or to just measure the energy content contained in that substance. Okay, and so here's what a calorimeter kind of looks like. This is kind of a janky drawing, but I'll show you a real one too. So this is like a vessel, and usually it's an insulated vessel, so that the only change in water, the only change in the temperature of the water comes from the heat that is being released from some object that's in there. So we don't get any heat energy from the outside environment into this water. So the vessel is full. It contains a known mass of pure water, and you also know the starting temperature of that water. And in our class, mainly what we talk about is the water warming up. Okay, so as the object either burns in the calorimeter or just cools off in the calorimeter, it gives off heat into the water. Okay, so as the water warms up, energy is absorbed by that water, and the energy absorbed by the water is equal to the energy that is released by the substance. Okay, and that's important to know. So here's a picture of a more realistic calorimeter, and this is called a bomb calorimeter. And basically, it's a insulated vessel full of water, and this little chamber right here, this one is set up so you can actually apply a little bit of an electric current to some sample. Maybe it's food item or something like that you want to know the calorie content of. And anyway, that causes this to combust and give off heat into the water, and the stirring rod just kind of keeps the water moving around, and you can measure the temperature change in the water. Okay, and the whole idea is that if we know how much the water changes temperature, and we know how much water was in the calorimeter, and we know the specific heat of water, we can figure out how much energy is absorbed by the water and relate that back to the amount of energy that was released by this substance. Okay, so let's just do a really simple type of question here. So here is kind of as simple as they get, actually. So if we have a 2.5 gram sample of some substance, we put it in a calorimeter, and it cools off. And the calorimeter has 1,000 grams of 20-degree water in it. The temperature of the water goes from 20 to 23. How much energy was contained in the substance? So here, we're just looking to equate basically the change in energy of the water to the change in energy of this sample substance. Okay, so here's how this ends up looking according to our math. We're going to be solving for the amount of energy, right, which is gained by the water and lost by the substance in equal amounts. So we're going to take our specific heat of water, which we have gone over. That's this number here, and represented by a C. This is the M, mass of water in grams, and this is our delta T. And that 3 just comes from the change in temperature of the water from 20 to 23 degrees. So that's our 3-degree temperature change. And so we can tell here that the water has absorbed 12,540 joules of energy. And that energy absorbed by the water means that there were exactly 12,540 joules of energy released by that substance. Okay, so that's kind of the most basic way to use a calorimeter. A little more complicated way is like this, where we're going to use calorimetry to solve for the specific heat of a substance. And this can be particularly useful if you're trying to identify some mystery elemental metal. That's the examples that we'll be doing. So I'll show you how this works. So we use it to identify these unknown substances. So here's our same calorimeter set up with our insulated container of water. The mass of the metal has to be known, but the identity is unknown. You heat it up to a known temperature. So this piece of metal in here that's going to be releasing heat into the water, we know the mass of that, and we know the starting temperature of that, and that's usually pretty hot. Okay, then it's allowed to cool off in a calorimeter, which you know, as the metal loses heat, the water gains heat and warms up. Okay, so let's look at a problem here. Kind of a longer problem. 0.7005 kilograms of some unknown metal, we're going to assume it's an elemental metal, is heated up to 390 degrees Celsius. Then it is submerged in a calorimeter containing exactly 1 liter of 20-degree water. The water warms up to 46 degrees, so that's a pretty good temperature climb. What is the specific heat of the metal, and what is that metal? So here's how you would go about doing this. You want to figure out how much energy is absorbed by the water. That's kind of what we did in the last problem, okay? And we know that the amount of energy absorbed by the water is equal to the amount of energy released by the metal, okay? So if we can figure out that energy, we can use the delta H that we calculate along with the mass of the metal and the temperature change of the metal to solve for the specific heat, okay? And sometimes the change in temperature of the metal kind of throws people off, and so this change in temperature of the metal kind of throws people off. So let's talk about that just a little bit here. So the thing to know is that as the metal and the water, you know, the metal cools off and the water warms up, they're gonna kind of end up being at the same temperature. And so the maximum temperature that the water gets to is equal to the minimum temperature that the metal gets to. And so we usually have the starting temperature of the metal given in the problem, and then the water temperature, you know, that the water warms up to is usually given in the question as well. And so the temperature change of the metal is just initial starting metal temperature minus the ending water temperature, and that will give you your delta T of your metal. Okay, we call that temperature that the water warms up to and the metal cools down to the equilibrium temperature. So let's go back to the problem, and we'll see how to set this up. Okay, so here's how I would do this. Okay, so here's how I would recommend setting this problem up. We want to use our same delta H equals Cm delta T equation, but we're going to make it look a little bit different. We're going to start with the Cm delta T and set that equal to delta H. So we've just moved the delta H from the left side of the equation to the right. That's no big deal. Okay, now this portion of the problem is for the water. And in particular interest to us is this delta H. We want to know how much water was absorbed by, how much energy was absorbed by the water, because that is also the delta H that's the energy released from the hot metal. And so we can set this up so that we can use the delta H that we calculate from the water as the delta H of the metal as well. And we're going to set that equal to Cm delta T. And so we're gonna use the delta H in both parts of this equation. And so we're gonna use water's values here to solve for delta H, and then we're gonna use the delta H along with the metal's mass and temperature change to solve for C, okay? And that sets up like this. We have the water, which has a specific heat of 4.18, multiplied by the mass of water, which is 1,000 grams. And then the temperature change of the water is 26 degrees. Okay, and that just comes from the problem, knowing that the water went from 20 degrees to 46, okay? And let's go ahead and solve that one up. That is, oops. So 108,680. Okay, so that's the number we care about. We want that delta H, right? So that delta H is now going to get used to calculate this variable C, which is the specific heat of the metal, along with the mass of metal, which we got to remember in the problem. It's 0.7005 kilograms, so that is 700.5 grams. And we got to use grams when we do the mass. And then the temperature change of the metal, so the metal starts at 390 degrees and then it goes to the equilibrium temperature of 46. So that is 344 degrees. And that's pretty typical. The metal will cool off by a lot of degrees and the water will warm up by a few degrees. That's just the way it works. Okay, so now to solve for C, and now we don't really even care about this stuff anymore. We care about solving for the C. This is the metal. So we're going to divide both sides by 700.5 times 344. Okay, so that number's on the calculator already. Divided by 0.451. So C here equals 0.451. Okay, and then you can cross-reference this specific heat, which is in joules per gram here. You can cross-reference that to a page in your Chem Bible, which of course I don't have, but you can search up this number and find that I think 0.451 is iron, I believe. So you know, you can match the calculated specific heat to the accepted specific heat in the Chem Bible and identify your metal that way. So anyway, I hope that helps with this type of problem.